Thank you everyone for being here. Hope you are having a wonderful day. Our day here is nice and well paced for our everyday lives, but days are a bit different around the solar system, and well, Mercury is one of those places where we find really interesting days. You might think you know Mercury. It's a rocky world that looks a little bit like the moon. It's kind of dead. Maybe you might even think it's a little boring. But in fact, there are a lot of really interesting things to discuss with regards to this little fast-moving world here. So let's jump right into it, starting with some basics, just in case there's some little facts you might not know on Mercury that are worth following up on. First and foremost, Mercury is, of course, the smallest planet in the solar system. It is actually smaller than two of the largest moons in the solar system, Jupiter's Ganymede and Titan that it orbits around Saturn. Those are both larger than Mercury, but they don't hold all of the records over Mercury. Anyway, more on that later, but there are no other planets that are closer to the sun as well, and being that it is so close to the sun, it actually gets within 1/3 the average orbital distance of the Earth compared to the sun. So it gets down to around 46 million kilometers away from the sun. And that really has some interesting dynamics for how it moves around the sun, because as you get closer to an object you're orbiting, you go faster, and that is what makes Mercury's orbit the fastest orbital velocity around the sun. And it means that the overall year for Mercury is only about 88 days. That is a Mercury year. And it, as such, being so close to the sun and lacking an atmosphere, has dramatic temperature swings, ranging all the way from well over 400 degrees C down to minus 170 degrees C. This is a huge range in temperature shifts. Fortunately, when it comes to the day and night side thing, again, the day is very different there, so it's not something that happens incredibly quickly, but it still happens quite rapidly nonetheless. So what I mean by that is it doesn't happen at a rapid pace, cold, hot. It still has a dramatic shift right at the morning and evening. But how does it actually work out to have a specific day there? Well, it comes down to a certain thing called spin-orbit resonance. And Mercury has a 3-2 spin-orbit resonance, meaning that as it moves around the sun, it will make 3 rotations on its axis for every 2 orbits. And that really makes for some really interesting and odd things happening on that particular planet. And so if you were on Mercury, you would be able to time from sunrise to sunrise. It would not be in that span of a year. It would actually be 176 days, about 2 years there, because that's how long it would take for you to actually orbit around twice and rotate on the axis 3 times. That is a subtle difference between a solar day, that is the sunrise all the way around to sunrise would be 1 solar day, compared to actually just rotating 360 degrees, something that is referred to as a sidereal day. Little details that you don't really have to worry about too much, but we will talk a little bit more about that spin-orbit resonance because it has some really interesting consequences. Moving right along to more historical aspects of these things. Where did Mercury get its name? Well, its name is the name of the Roman deity of a number of things: commerce, eloquence, messages, communication, and travelers. It is the end result of a really interesting path on naming, and to really understand it, you got to go back to at least the first recordings of seeing this particular planet, and where it was noted at least as far back as the 14th century BC in Assyria, where it was actually referenced as the jumping planet, likely because it appeared to go from one side of the sun to the other relatively quickly. But it was also recorded a little bit later by the Babylonians in the first millennium BC, where they actually named it after the god Nabu, not to be confused with the Star Wars planet. But this particular deity was a messenger deity, and that particular theme is what carried through the naming of this planet through the different cultures. So, looking across the oh goodness, My geography is blanking out on me. Anyway, the area of Asia Minor, jump across Asia Minor into Greece, and you actually have the Greeks coming up with some names, at one point calling it Stilbon, meaning the gleaning. However, it was also referred to as Hermes there, where Hermes is the Greek god of trade, commerce, roads, thieves, and athletes. But Hermes, again, is actually a messenger deity, and that is where Mercury comes from in Roman mythology. Mercury is the Roman equivalent of Hermes, and so the messenger theme made it all the way through, all the way over there. And you might be familiar with the symbol of Mercury, that is the caduceus, which is shown, he's actually holding one right there. That is a staff that has two serpents coiled around it, has some wings at the top. You might have actually seen it on medical equipment or ambulances and such. How it got associated with that, well, that's a little bit more complicated of a story, but nonetheless, you might have also seen the symbol for Mercury. It's not the symbol for Venus with horns. That's kind of what it might look like at first glance. It actually is meant to be the caduceus with two coiling snakes going up above a staff. So that is what you should see when you see that funny little thing, not the evil form of the Venus symbol. So anyway, moving right along. Mercury, of course, is the innermost planet. As I mentioned, it is also the innermost of the four rocky planets, the terrestrial planets. And the others, of course, are ones we're very familiar with. Venus, the one we're standing on here, Earth, and Mars being on the other side of us there. They are really interesting worlds as a category, and they all are lacking in rings. The rings at other gaseous planets, those ones, sometimes they're nice and really prominent. Sometimes they're rather subtle. In the case of Jupiter, we didn't know it had rings until we went there with the Voyager spacecraft. So yeah, some of them are much more subtle. They aren't all like Saturn, but actually all of those gaseous outer planets do have some measure of rings. Now, among these four planets, there are only 3 moons, and 2 of which are basically just very likely some random captured space potatoes. That is, asteroids that might have been captured by the planet of Mars. The only really substantial moon in the inner solar system is the one that orbits our home here, the one that earned the moniker of the entire category of these things, the moon. But Mercury and Venus don't have any moons because, again, all the moons are kept here around the Earth or around Mars, which, got some discount borrowed moons from the asteroid belt. Moving on to the interior of Mercury, it is always really interesting to start discussing how this is a very different rocky world than the others, and it comes from the actual interior structure. We know it has a solid silicate crust and some form of mantle, just like the Earth has a magma mantle beneath us. Its mantle here is a little bit different. It's actually substantially a smaller volume of the planet. Inside that, there is an iron sulfide outer core, a large core of a lot of iron primarily, and deeper inside there will be a liquid core that is likely even more iron and other materials, and even deeper still there's likely a solid core. So the core itself is a bit of a complicated structure, but this is where we come back to those moons that are larger than this particular world, because while this is smaller than Jupiter's Ganymede and Saturn's Titan, it actually is more massive than either of them. And that is an interesting thing to note. If you follow the math on it, you'll realize that the big difference is that this world is rather dense. It's actually second only in density to the Earth, with Earth having 5.5 grams per cubic centimeter on average for the density of this planet beneath our feet, where Mercury is at 5.4. So it's just barely less dense than the Earth, and that is still something that is really an important thing, and it leads to some interesting mysteries I'll mention again in a moment. But as we're looking in, we see, again, a lot of liquids, and in particular, liquid metals, and that leads to some interesting outcomes. Again, Mercury being mostly metal compared to its silicate materials really gives it a different composition than the other worlds here in the solar system, and as such, planetary scientists trying to estimate the size of that core in there think that it actually takes up 55% of the volume of Mercury. Again, that is dramatically different than the other planets. The core of the Earth, for example, only fills about 17% of the planet we are standing on. And this iron core appears to have a lot of molten iron, and that allows for a potential to develop a significant magnetic field. I say significant, it's not actually as strong in many ways as some other planets, but it is nonetheless detectable, which is more than I can say for some of the rocky planets here in the solar system. Not the Earth. The Earth has a good substantial one. It's very helpful for us. But the other planets like like Venus and Mars, they don't have a very substantial magnetic field, and that's a problem for a number of reasons. But again, the core of Mercury has a ton of iron in it, and it leads to a very specific question, one that is really simple. Why? So why would it actually be this way? And that is a difficult question to answer, and we've been looking at it for a while, and we actually have a few different hypotheses on how Mercury would end up like this, being much more dense and have a much larger core compared to its mantle, compared to the other worlds. One hypothesis is the giant impact hypothesis. In general, when it comes to planet formation, it often comes back to, well, could you smack it with something and make the outcome end up be what you think it is going to be? And often the answer is yes. So that is, of course, going to be one of our hypotheses here. Did something really large in the early system smack into the forming Mercury and strip off everything but the densest materials? That is one possibility. Another is actually more gentle. It is actually saying that perhaps Mercury actually formed to be a much larger planet, but the solar wind actually blew off a lot of that remaining material because of its proximity to the sun, the increased intensity of the solar wind, and the fact that the magnetic field at Mercury isn't so intense that it would actually prevent the loss of some of these materials. Perhaps it got blown away. And there's another idea as well. The idea that, well, perhaps you didn't need the sun to actually blow off this material. Perhaps the nebula that formed the actual protoplanetary disk actually had sufficient drag in it that as Mercury moved through it, its outer atmosphere got stripped away. These are all interesting hypotheses, and we are really interested to try and find the answers to which one of these would actually be correct. The way you end up with a good hypothesis is to actually go and make it one that could be falsified. Go out and say, okay, if this other fact isn't true, then this entire hypothesis can be put on the shelf of history and referenced as an interesting idea. We'll have a couple of those in a few minutes. But this is something that is really useful. However, those tests that we would need to be able to say whether or not one of these was not true or one of these are likely to be true, well, we need more data on that. We need to go take a closer look. So we are really wondering about it, and I'll talk about how we're heading there a little bit later. So let's actually look a bit more still on the past of Mercury. There has been a lot of things that have gone on. Again, that early part of Mercury's history we're still trying to figure out, but there are some other parts that we do have a good idea on. In particular, Mercury formed about the same time as the other planets, roughly 4.5 billion years ago. But in the time after that, there was, well, after it had lost its outer material, or however those three hypotheses, whichever one of those happens to be true, after that point, you end up with a world that doesn't have a substantial atmosphere, which can then be smacked really hard by some really large rocks, and that allows it to end up being incredibly heavily cratered. And there was a period of what is called a heavy bombardment that occurred shortly after that time frame, and then fast forward a few 100 million years, and then it gets bombarded again. We know this because we actually look around the solar system and we see this specific pattern in the way things are impacted, and that is why we believe there's these two different periods of bombardment, leading to the second one being named this nice inventive name, the Late Heavy Bombardment. But yes, this is a second period in actual interplanetary history that is really interesting, and it is really marked by the fact that we can actually look around the solar system and see a number of cases where some bodies were impacted by a lot of extra objects. So that would be the late heavy bombardment. But during that particular time, Mercury wasn't just any simple dead world. It actually, again, was being bombarded while it was actually active and had volcanism going on, that is volcanic activity. And so in that time frame, if you have a planet or moon that gets hit by a very large object, there's a good chance that you'll end up with a big flat plane afterwards, because you will punch right through the mantle or right through the crust into the mantle, and that whole area will fill with lava. That is something we see on the moon. That is where the seas of the moon are. And on Mercury, its largest basin, the Caloris basin, is actually something that would have been formed by having it fill with magma after a dramatic impact. Now, that name Caloris is one that is interesting. We'll talk more about naming things on Mercury in just a second. But again, these are similar to what we see on the moon. The mares on the moon, or the seas, they aren't actually water-filled, but again, they are nice and flat. They're actually like plains on the surfaces of these worlds. Now, when looking at Mercury, of course, it is very easy to want to compare it to the moon, and there's many reasons why you would want to. First, it has a lot of similar features. It has, again, a lot of heavy cratering, extensive plains, and a lot of non-activity going on there. It looks rather quiet, and it has a few other things that are really specifically familiar when comparing to the moon. You see mountains, plains, escarpments, and valleys, very specific features that all look very reminiscent. And so, yeah, there's a reason why a lot of comparisons are made. But again, the moon is nowhere near the density of Mercury, so there's something very different on the inside of these worlds, and their sizes are actually substantially different as well. So when we're actually looking at this particular world, there are a lot of features, and it is worthwhile to name them. There are a few exceptions to the naming conventions, and that is because some surface features were actually named prior to these conventions being named. For example, you actually have craters that are all named after deceased artists, musicians, painters, authors, and other people in the arts. And so you have a number of different places. For example, there is a Lovecraft crater down on the southern pole of Mercury that is actually right near the pole, to the extent that inside that crater is in perpetual darkness. And so it makes sense to name that particular crater Lovecraft after H.P. Lovecraft, the writer who really focused on horror in his genre. So I could easily see a nice sci-fi movie taking place down there in that particular crater that has a lot of reminiscent things from his works. I would love to see that happen, even though I don't really care to watch horror movies. Anyway, there are a whole bunch of other types of features. Ridges are named after scientists who really contributed to the knowledge of Mercury, while depressions are actually named after certain architectural works, and plains are named after various languages various language names for Mercury. You look around, you find a whole bunch of different cultures that actually came up with their own names for Mercury. So yeah, it's good to actually put those names on that planet in some shape or form, and that's one of the ways they do that. However, again, there are some exceptions there. Caloris Basin is one of them because Caloris is actually short for calorie. Yes, it's the thing that actually is involved in dietary things. It's a unit of energy, and in particular, one that is very related to heat. And so it made sense to put it on this scorched little rock, and thus the Caloris Basin got its name. Then there are valleys which get names of abandoned towns and cities and other settlements. And then there are escarpments which have all sorts of fun little names, some that start with HMS, others with USS, because they're all named after ships that went out on scientific expeditions. But again, there's a whole bunch of really interesting names, and I could easily see a whole bunch of science fiction or other fun media outlets using these names for their advantage. For example, I could easily see this particular crater right in the center of the image here being used in the next Marvel movie, because that particular crater is named Kirby Crater after Jack Kirby, one of the most prolific artists in the Marvel comic books over the years. And so that particular one, yeah, I would laugh hysterically in the theater by myself, because I would know that they set it up in Kirby Crater and no one else in the theater would, and that would be fun. Anyway, on to actually moving off the surface and really talking about what else makes this world really unique? Well, the object itself, of course, has its unique features, but its orbit really stands out from the rest of the planets in the solar system, and it took a while to really understand it. We looked at it for millennia before really actually understanding something incredibly fundamental like its actual shape. And so starting in the 1500s, you have Tycho Brahe. He was a German astronomer who took incredibly precise measurements without using a telescope, likely the most precise measurements ever taken with the human eye without magnification of the astronomical bodies in the solar system were likely done by Tycho Brahe. And his apprentice and actually successor was the man shown there, Johannes Kepler, who actually used that particular data set, which included very specific observations of the planet Mercury, to actually determine its orbit. And what he found was something that was profound at the time, and that was that the orbit was not perfectly circular. This is something that doesn't take much effort to do, I will say, because I've actually done this a few times, and I've actually taught students how to do this. They might not think it was actually that easy to do, but nonetheless, you can take just a small set of Brahe's observations, his actual observations, and plot it on a sheet of paper and get a reasonable value for the shape of the orbit of Mercury. And so Johannes Kepler could not ignore that this was not a circular result. He actually used that as one of his first of the 3 laws of planetary motion, and that is that planets orbit in ellipses. More on that in a second. But after Johannes Kepler, we had also Sir Isaac Newton making a whole bunch of different observations of the physical world and came up with the laws of gravitation, in particular the universal law of gravitation, which has incredibly profound uses. We still use it today, even though we have slightly more accurate calculations, but all the spacecraft going up into space are using a lot of Isaac Newton's work. Now, there's, again, one thing when I say there are more precise things. Yeah, we realized they were more precise because, partly, we looked at Mercury. When we looked at Mercury, we found that despite all of these specific things we had found, Mercury doesn't exactly play by the same rules as what we learned by these particular individuals. So it is a worthwhile thing to see how did they actually see some differences there. Well, again, first we have to understand what the orbit actually was, and that is, it is an eccentric orbit. And so what is orbital eccentricity? It is simply a measure of how non-circular a particular loop is. In particular, if you actually have a nice circle, we will say it has an eccentricity of 0. That is a perfect circle. If you start to squash it and stretch it in a certain way, it then becomes more elliptical, like the red loop over there. And when we're looking at that particular notion, well, eccentricity then has a value between 0 and 1. For example, 0.07 would be a very nice ellipse. And if we go up to 1, we end up with the green line, a nice parabolic arc. And then if you go above that, you end up with a hyperbolic arc. And these are all fun things that are referred to as conic sections and a whole bunch of other information you don't need to know to understand this, but it's fun to talk about. And I will be happy to answer questions on it anyway. But yes, we actually have very specific shapes of orbits as objects come into this particular solar system. Now, as that is happening, if you've ever heard us say we found an object that originated from outside the solar system, well, this is one of the ways we find out about it. We actually measure the eccentricity of the orbit. In particular, we try to determine if we have something that is less than 1 or greater than 1, because if it's greater than 1, it came into the solar system with some significant velocity, and it's not going to stay. It's going to pass right on through. That is how you can actually get a good idea that something likely came from outside the solar system. Not true 100% of the time, but it's pretty much a prereq for the different objects that you might have heard of, such as Oumuamua, which passed through our solar system a couple years back. Anyway, going back to Mercury itself, it does have an elliptical orbit, and we can measure its eccentricity. It comes out to around 0.21, and it's the most eccentric of all of the planets. Now, 0.21, you'll notice, is substantially less than 1, which means it's not really distorted like the red ellipse there. It actually is much more circular in appearance, so it helps to actually draw this ellipse in a certain way to really emphasize just how elliptical it actually is. And so here's a nice diagram to do that. And again, this is a very nice elliptical orbit, which has its furthest distance from the sun up here at 70 million kilometers, and its perihelion at around 46, and that would be this point down here with the sun right in the center there. So this particular diagram, as is shown here, it is illustrating a very specific orbit of Mercury. In particular, back in 2006, one of the orbits Mercury had in that time frame that went between May and July, roughly. And so that is not any generic orbit that's being shown there. It's a very specific one. There are a few other things that are being indicated here. In particular, you might be able to notice that the left side of this orbit is actually shown in a more orange color, while the right side is more yellow. That is important because the yellow indicates where Mercury is above the plane of the Earth's orbit, and the orange is where it's below. We'll talk more detail on that because that is surprisingly important. And to get some orientation on here, there's one more line in here that points out to the side. If you were on Earth, as we all are, on about March 21st, the sun is in a very specific direction, and it is in this direction. So, in other words, we would be up and to the right of the image here on March 21st, looking straight back through here. That is the date of the March equinox here in the northern hemisphere, the vernal equinox, the beginning of spring, and a very important reference point for us in astronomy to actually orient everything. So, if that is the direction of March, then, in other words, we're over here in March, then when we're up at the top, we'll be a few months later towards May, and towards the bottom will be a few months after September, leading us towards November. More on that later. But the last thing to note on this particular diagram that really helps out here is if we take half the length of this line here, what is called the major axis, half of it the semi-major axis, and we turned it into, use that as the radius of a perfect circle, what we would end up with is the white line here. So you can actually see how much this orbit deviates from a perfect circle around the sun there. And that really results in some really interesting things. Again, the way you actually move around things actually impacts your speed. As I mentioned early on, Mercury moves around the sun the fastest because it's the closest there, but it also goes closer sometimes and ends up further away at other times, meaning its speed around the sun changes, and it changes quite dramatically at times, and that's where we get some rather surprising consequences. In fact, if you go to a certain part of Mercury, you might be able to spot a sunrise that looked a little peculiar, something a bit like this, where it goes up, and you know what, the sun doesn't want to go up. Oh no, it changed its mind, and it actually then moves on up. This is actually something that can be seen from Mercury. You can actually watch the sky actually move in a really interesting way, where the sun will actually wobble in the sky, go up, go back, and move on. And from this particular site on Mercury, which is in Mercury's northern hemisphere, if you look the other way, one orbit later, again, with spin-orbit resonance, we end up with something very specific. That means that if the sunlight is what's on me and I'm on Mercury right now is noon for me. One orbit later, I will be facing this way. One orbit later, I will be facing this way. Thus, I will have rotated actually on my axis actually 3 times, but in 2 orbits. And so what that means is if I actually watch sunrise at one point where the sun wobbles, then 1 orbit later, I will see sunset on the other side when the sun makes its wobble again. And so sunset from that particular place looks a bit like this, where you actually see the sun say, I don't want to set. Oh, okay, I'll set now. Seems like a small child getting to a pool, and they're worried it might be a little cold, and so they're rather hesitant. And so the sun will wobble on either side of the sky there, or anywhere on the surface of Mercury, you might be able to see some wobble at some point in the sky, not necessarily at sunrise and sunset. But keeping with the sunrise and sunset example, we can actually figure out what is going on here, and it really has to do with what we were seeing with the shape of Mercury's orbit. Again, we can actually see the sun rise up, and from a slightly different spot than where we were imaging before, you'd even be able to see it poke up above the horizon, set back down, and then come back up above the horizon. And that would happen all in the same Mercurian day, which again is 176 Earth days. And so it is worth understanding that in that time frame, yes, again, Mercury will orbit around the sun twice to give you that same wobbling sunrise. Again, if you find a spot on Mercury where you get a wobbling sunrise, you'll get a wobbling sunrise the next day as well, because it always has that specific orbital resonance where you'll have the same orientation of the planet every other orbit at the same spot. And so, as the sun actually does stop in its motion across the sky, the reason it stops is actually because of how the planet is rotating around its axis and how it is revolving around the sun. And so about 96 hours before it gets to its closest approach to the sun, it actually will have its rotational velocity match its orbital angular velocity, and so the sun will come to a stop in the sky because the rate at which it rotates is matching the rate at which it's moving around the sun. This is very similar to what we see with the moon. We only see one side of the moon because it rotates at the exact same rate at which it revolves around the Earth. This happens at a very specific point in time on Mercury, and so this is one of those 2 points at which it happens. After that point in time, well, the actual orbital angular velocity is faster than its rotational velocity, so the sun actually appears to move back down towards the horizon, again in this specific sunrise example, and so you would see what is referred to as retrograde motion, the sun moving in the opposite direction of the way you expect it to, and it actually can go backwards and even set if you're at, again, a very specific place. So the sun is set. What happens next? Well, you saw what happens next. It starts rising again, but that comes after perihelion, when the planet actually moves far enough away that its orbital angular velocity decreases to the point that its rotational velocity again is faster, which allows the sun to move across the sky as normal. So this is how we get that little wobbling dance that we see, and it is something that has actually been very useful for us to understand. Again, the motions in particular right around this point in Mercury's orbit actually led to some fascinating new physics and allows for a test of a lot of new and interesting things. In particular, when we're looking at Mercury's orbit, we see a certain type of precession. And in the 1850s, we had Urbain Le Verrier. I'm sure I'm not doing that pronunciation well, but I gave it a good shot. Anyway, he realized that Newton's particular calculations didn't present an exact result of how the orbit actually changes over time. What do I mean by that? Well, that point of closest approach to the sun, it shifts over time relative to that random yellow line I pointed out. That was the vernal equinox here in the northern hemisphere on the Earth. That line is a good reference point, and the perihelion of Mercury shifts over time very slowly on the order of around 1.5 degrees per century when measured relative to the Earth, and Newtonian mechanics actually didn't give that exact same number. This might seem like a trivial, probably error-related problem, and if you think that that is likely the case, you probably have some good kinship with my students who thought the drawing of the ellipse was too hard. It is actually possible to get these kinds of measurements, these very precise measurements. It takes a lot of effort and intentional precision, but it is nonetheless possible to see a difference of 1/100th of a degree per century, and to be able to actually figure out that that is a problem there. And so Leverrier was trying to figure out why there would be a discrepancy, and he was actually using something that was really notable right at that period of time. This was shortly after the discovery of Neptune, where they discovered it by seeing that Uranus had some interesting perturbations in its orbit. And so when looking at that, people were able to predict where Neptune should be, and it was discovered very quickly after the predictions were made. So the idea that a planet could be within the orbit of Mercury, actually perturbing its orbit, was an interesting idea. And so eventually this planet got named Vulcan. Again, same root as volcano, which is something that is, has to do with a lot of heat, volcanism, all that really dramatic stuff. And so Vulcan was the proposed name for this world. It was never found, and it does not exist here in the solar system. It does exist in science fiction, in particular in Star Trek. That name was used again. So that is where Spock's homeworld happened to have a bit of history in its ideas here on the Earth. That was where the name Vulcan for a world really did come from. So, that is interesting that there was a proposed world, but if it was never found, what was the solution? Well, about 60 years later, actually less than 60 years later, Einstein proposed his theories of relativity, and it actually had some implications for the actual precession of Mercury's perihelion, its actual motion. It's very minor, but the idea of general relativity is that gravity is actually a distortion in space-time, and it is ever so slightly different than Newtonian mechanics in its actual predicted outcome, that this could actually determine or could describe the difference that was found between those two measurements, the Newtonian predictions and the actual measured results. And in fact, it was incredibly precisely the exact thing that was missing. We now have much better accuracy on all the measurements of why the actual perihelion of Mercury moves ever so slightly over the course of 100 years. And we've actually refined this a number of times. In 2018 in particular, Clifford Will over at the University of Florida developed a few more calculations and other things that added slight corrections to it. And the corrections, again, they were incredibly minor. So minor that, their corrections were about 1 degree every 2 billion years. It's very minor, but again, we can actually measure these things. These are really big objects. They are incredibly hard to measure these things, but it is nonetheless something that we are able to do, and that is another good proof that, the theory of relativity very, very likely is actually valid. It's so out there in some cases that we test it over and over and over again, and we're going to test it again before the end of this talk, or at least talk about doing some tests on it. But again, more on that later. All right, with regards to doing those tests, we run into actually trying to explore this world, and that is where some problems arise. Some problems in particular come from, its location. It is, of course, really scorched. It is so close to the sun, and that makes it difficult to get to. You might think, we're just going inside our orbit. That's got to be easier than going out to the distant planets. Not necessarily. Again, think about that notion of if you get closer to an object, you orbit faster. So if you take a spacecraft and try and slow it down enough that it will arc into the center of the solar system towards Mercury, it will be going much faster than Mercury when it gets there. And that creates a big problem. If you actually want to slow down there, it is a big challenge. And even if you do get there, the fact that you are closer to the sun, you end up with some interesting tidal effects that can throw off orbits. And again, its actual slow rotation leads to some really interesting temperature changes. So if you put something down on the ground, you're going to have some problematic things for your spacecraft, including trying to actually generate power over an 88-day night. That is a long time to be able to operate on batteries. So it is a big challenge to deal with a long night. on top of the fact that you have incredibly cold temperatures. One of the things you need to do with electronics on a very cold night is you have to keep them warm. And so you have to expend energy. You can't just turn it off and have an alarm to turn itself back on. No, it has to be kept warm to be able to actually function well. So this is a notable problem. And then again, since it doesn't have an atmosphere and you can't actually use a technique called aerobraking, which is going into the atmosphere just a bit around a planet to actually slow yourself down. This is used a lot when going to outer planets, going out to, say, Mars or even Jupiter or Saturn. You can actually take a spacecraft and go into the upper atmosphere, slow it down a little bit, just catch a little bit of that drag, and use that to capture yourself into the orbit of the planet. And then once you're out at the far side of the orbit, you thrust a little bit to make it so you don't keep going back into the atmosphere, and then you've caught yourself in a nice orbit. It's a technique called aerobraking. So again, since Mercury doesn't have an atmosphere, you can't use that nice fuel-efficient technique. You got to take all the fuel there, and that makes it much harder to actually slow down effectively. So how do we actually get there? Well, we took a long time to get there. We swung by it a few times. In particular, there have only been 2 missions that have actually made it to Mercury so far. The first was Mariner 10 back in the 1970s, and the second was the Messenger spacecraft, which flew by the planet in around 2008, 2009, and eventually went into orbit in 2011. It was there for a little while, but it is always an interesting thing to note just how big that time gap is, just trying to get to this world. Its big challenges really held off some of the intentional exploration of this world. And there's actually another mission on its way there right now. That is the ESA, the European Space Agency's Bepi Colombo mission is on its way there. It is aiming to get there in 2025. Yes, it launched last year. It's going to take until 2025 to get there, despite the fact that it is much closer to us than, say, Saturn is. It is a very nearby planet, but all of that extra energy you carry into the center of the solar system, you have to find a way to bleed it off. And so that is why it's so hard to actually slow down enough to actually get around this particular world. And as such, there have been good reasons to do some more ground-based observations. In particular, the 1.5-meter Hale telescope and the Arecibo radio telescope over in Puerto Rico. Those have actually been involved in some mapping of that particular world. You can do some measurements from here quite readily, but of course it's always better to get nice and up close to these objects. And so back in the 70s, we had Mariner 10 on its way there, and it was actually not just going to Mercury, but it also was intended to go by Venus, and that notion in and of itself really earned it a moniker of holding a lot of firsts. In particular, it was the first probe to actually fly by multiple planets, and as it was trying to slow down, there is a technique to actually slow yourself down to get closer to objects, and that is a gravitational assist. That is, as it flew by Venus, you go in a certain way that Venus's gravity tugs on the spacecraft, and you can actually use that to speed your spacecraft up or slow it down or just redirect it. And so this was the first spacecraft to really do that, and it was really important to do that because it allowed us to actually have the Voyager 1 and 2 missions be successful, because those missions relied incredibly heavily on gravitational assists, as have a lot of other missions since then. But in particular, Voyager 1 and 2 had multiple gravity assists all the way out into the outer solar system. So it's a worthwhile thing to note that this little spacecraft, Mariner 10, was really key in actually making sure we can, well, be good mariners and sail around the solar system. So that is one of the reasons why these particular spacecraft were made, launched, and that in particular, though, was secondary, of course, to the main missions, where the main mission at Mercury was to do some good science. They wanted to measure environment, atmosphere, and other surface characteristics, and they did quite a good amount of that, as well as got the first close-up pictures of Mercury. But as they did that, they did not get a full map of Mercury, and that's something that I will remember for, well, my entire life. I grew up in the 90s, so in the intervening time between Mariner 10 and Messenger, For a significant fraction of my life, I only had half a map of Mercury, and you might be saying, oh, this silly young kid only had half a map of Mercury. Well, I know. It is still a interesting thing because, well, Mercury might be one world that we've only just recently, in the last really 10 years, gotten images of all of the sides of this planet. It is still nonetheless a good example of just how much there is out in the solar system that it will take a lot of effort for us to really explore in detail. We've flown by a few things, we've actually orbited a few others, but there's so many other things to explore and to learn about. Anyway, fun side note aside, the secondary planet objectives of Mariner flying by Mercury, again, was to actually make sure it can run experiments between planets as well as do those gravity assists and make sure that we can actually sail through the solar system effectively. And you might think, okay, they led to the success of Voyager 1 and 2. Well, Voyager 1 and 2 weren't just Voyager 1 and 2. They were actually renamed from Mariner 11 and 12. They were renamed that because after Mariner 10 and its success, we actually realized, yeah, we can use this method. We can go around the solar system effectively. We aren't just going to visit a couple of planets. This is an outright interplanetary voyage, and so that's how Voyager 1 and 2 really would get a different name, because they really were an entirely different era of exploration, just because we'd figured out how we can move around, and Voyagers were going to take advantage of that. And you can thank Mariner 10 for really making that possible. All right, so Mercury flybys of Mariner 10, it had 3 of them. The first one actually got really nice and close, so it snapped a few of the pictures over there. The second one was quite a bit further out, but it went around the southern hemisphere, so it got a few other pictures there. And then the last one that it flew by got really close, only 327 kilometers over the surface of this object, and so it got a few really good detailed pictures, but again, it only mapped about half the planet in that set of 3 flybys. So it was a really successful mission, but it was limited by the fact that it could only fly by it. It could not effectively slow down to go in orbit around it. So, advance quite a bit up to the Messenger spacecraft, where Messenger is short for Mercury Surface Space Environment, Geochemistry, and Ranging. Yes, it's a fun little acronym there, and that particular one, they are definitely thinking of radar when they added the and ranging. In case you don't know, radar is just radio detection and ranging. So yeah, fun bit there. Anyway, Messenger, of course, it actually was able to get into orbit, and it did so in 2011, and it did that through 2015. And the mission itself was much more detailed in how it was looking at Mercury. It wasn't just meant to identify surface features. It actually wanted to look at the chemistry and the geology of this particular world. And it had to go on a nice circuitous route to get to that orbit. It had to perform a lot of flybys. It actually went inside the Earth's orbit, swung back by, and did an actual gravity assist at Earth, and then it flew back by Venus twice for 2 gravity assists, and it even used Mercury thrice for more gravity assists to actually get rid of a lot of that energy. It took so much effort to slow this spacecraft down, and then it was finally able to actually expend a little bit of fuel and go into orbit. That is a really big challenge, and it was a very worthwhile thing to have done, because we got a lot of really interesting information from the Messenger spacecraft. So the Messenger spacecraft, again, it had a number of flybys. It went by it in 2008 when it actually got within 200 kilometers of the surface. And then it went by in 2008 again in October, and then in September of 2009. Then 2 years later, it was actually able to go into a nice stable orbit, a very elliptical orbit. This time not an elliptical orbit around the Earth, but around Mercury, where you have its closest approach down at 200 kilometers, while its furthest point from Mercury was all the way out at 15,000. And so it took 12 hours for this spacecraft to go around this little world, and that was really actually a quite effective way to get a lot of information on it. But one spacecraft in a few short years is still somewhat limiting on what we can learn, and so the Europeans and actually the Japanese have launched the Bepi Colombo spacecraft, which is named for Giuseppe Bepi Colombo, who actually was the one who proposed the gravity assist that would be used by the Mariner 10 spacecraft. So hence the name of this spacecraft. And as I mentioned, it's a joint mission by the Europeans and the Japanese. The ESA, the European Space Agency, and JAXA, the Japanese Aerospace Exploration Administration. And so they were working together to build this, and they are working together now to operate it. And this particular mission is the one that is looking at that particular question I mentioned earlier on how you end up with such a dramatically different interior of this world compared to others. And so they want to actually make sure they can actually resolve the differences between these particular hypotheses and try and rule out the ones that aren't true. So that is a neat thing to be able to do, and I'm very excited for how this particular mission will be moving forward. And it's going to take a little bit of patience for this one because it'll get there in December of 2025. It takes quite a while again, so it is going to be taking its own circuitous route over there, and so it will take a while to actually slow itself down enough to be able to get into the orbit of Mercury. But the orbit it will take is not one, but two, because it will have two spacecraft. As you saw in that last image, it actually separates once it gets over into orbit, and the two spacecraft that are there are the Planetary Orbiter that was developed by the Europeans, and the Magnetospheric Orbiter, which is the one that was developed by the Japanese. And so those two will actually study the magnetic field as well as the interior there. So they get to do dual duty on this mission by actually spending a lot of time out there. And again, it's going to take a long time to get there in a nice circuitous route. It's doing an Earth flyby, 2 Venus flybys, and 6 Mercury flybys to slow itself down. So again, it takes so much effort to slow down a spacecraft going into the inner solar system. That is why it is such a challenge to really get anything to this world. And so the objectives of this mission are somewhat clear. Again, we want to actually look at what happens to a planet that is very close to its parent star, as well as look again at the interior and try and answer some of those questions there. And we also get to get some good views of the surface and learn some things about that along the way. And we also get to look at the outer portion of, well, it doesn't really have a substantial atmosphere, but there are some particles there that can actually be detected. And so we actually get to study that in particular detail. And we also are really interested in that magnetic envelope, the actual magnetosphere of this particular world, as well as, again, trying to look at the origin of it. We want to understand the core as best as we can, and it helps to actually have a spacecraft there to actually make measurements. So that is one of the big things that the Japanese section is really looking at there. And of course, we always want to verify Einstein's general theory of relativity by looking again at more really interesting parameters there. So it takes a lot of effort to verify Einstein's theory of general relativity. We do that repeatedly. And repeatedly. I might be repeating myself there, but anyway, yeah. So we are always wanting to make sure we're understanding the universe well, and that's one key thing that will allow us to do yet again. Now, this is a lot of really interesting things. We've talked a lot about a number of different things about Mercury. It is, of course, a really small, fast and scorched world. It is moving quickly around the sun, and it is quite small. It's a neat little place with a really fantastically unique orbit for a planet. It has the greatest eccentricity and thus the most dramatic changes in its speed around the sun, and as such we get that wobbling effect that is visible from just about everywhere on the surface of Mercury. You don't necessarily get that nice sunrise-sunset effect, but you do get to see it really clearly, and one solar day there lasts 2 Mercurian years, so that gives you a really interesting schedule. I don't think I would want to be up for that entire day. And we wouldn't be able to. It would actually kill us, so we shouldn't do that. But we are also able to, with this particular planet's orbit, really test early on Einstein's theory of general relativity. And that is a really important thing for us to really understand, because it can actually have profound impacts on how we understand the rest of the universe. So it's very useful for this little planet to to actually give us all of that information. So yeah, it's not bad for a nice little planet. And this particular planet has something really nice in store for us in just a few short days. Because, well, think back to this particular diagram I showed you here. Yeah, you remember that one? We actually had that specific color issue going on there where we had orange on one side of the orbit and yellow on the other. That is where one half is below the plane of the Earth's orbit and the other half is above it, leading to a really important couple of points, the actual transitions between that. And the transitions, which are called the nodes ascending and descending, those allow for something really special. In particular, the bottom one, as I mentioned, is pointed towards where, if you draw a line out from the sun through that point down towards where the Earth will be, it'll point towards where the Earth is in November. Given very precise alignment, you get to see something really special. In particular, if we're looking here from the Earth and we have all these different orbits shown, the red one is Mercury's orbit, and this is actually just a few short days away. On the morning of Veterans Day, we'll get to see something nice, and by morning, I mean very early morning. Here we are heading towards sunrise, and as sunrise happens, well, if we take a very close look at the sun, we will see a transit of Mercury. Mercury will move across the face of the sun because we are at a very precise point, and this alignment of three celestial objects has a really fun name. It's called a syzygy. But in this case, this particular event, being able to see it, is even more special because it's very rare to actually get a good transit. And yes, this particular transit will be ongoing from before sunrise on through about 10 a.m. Pacific Standard Time here on Monday. And so that is a really neat thing. Just don't stare straight at the sun. It's a bad idea. So don't do that. But instead, we do have some nice equipment here, and we are actually going to be live streaming online that morning. We will actually set up our solar telescope over in the observatory and send it over to the sun, and we will put those images online in real time for you to actually be able to see how this particular event is ongoing. So we will be going from about 7:30 to 10:15 because 7:30 is about the earliest we will be able to actually get our telescope on target. So that will be the time frame we're doing that. And you won't want to miss this because these are quite rare events. The next one is occurring in 2032, but you aren't going to be able to see it from here. Likewise, in 2039, you will not be able to see the transit from here. The next time you will be able to see a transit of Mercury from this site is 2049. So I'll be well down my career path by that point, having a lot of fun here. But that is something that won't be for quite a while. So I really would love if you guys joined us online on a Monday morning because we are going to have a lot of fun taking a close look at this wonderful, unique, and fascinating world. Thank you.